Hello everyone, my name is Gajivan Rajanayagam, and here are to present my 6 articles that I've picked. My first article is that was then, this is now, our security evaluation of password generation, storage, and autofill in browser-based password managers. Here we are looking at, the researchers looked at 3 aspects of the password manager: is generation, storage, and autofill, and they have categorized them between 3 different categories: browser-based, extension-based, and app-based. And the first gap they identified is the autofill feature, and there were some cross-site scripting attacks that was trying to empty someone's vault. All password managers should refuse to submit passwords into iframes, only submit credentials over a secure channel, and also should require some kind of user interaction to avoid these type of attacks. It's like any random number generator. It generated some weak passwords, and it all went away when the length was increased, and only KeePass and Dashlane make use of symbol sets, the majority of the symbol set, and the rest of them use very minimal amount of symbol set. And also when the password, the default setting should be restored, meaning like if you have to generate a weak password for one website, that shouldn't become the new standard for all the other passwords that you're generating. It should automatically go back to your 16 or 20 digit 20 character password. Storage of the password, master password should be strong, and this is the master password is typically used by using the KDF function to create the encryption key, and this is done by the app-based and also the extension-based providers. However, the Chrome or the browser-based ones lacks the storage capability, as well as they do lack the capability for generating the passwords as well. And just to summarize, like it should always require some kind of user interaction to fill the passwords, and should have a universal master password policy or like a standard across all of them, and it should all filter out weak passwords and generate. Practical decryption exfiltration, breaking PDF encryption. In this paper, researchers found two vulnerabilities within the implementation of PDF encryption. One is the partial encryption, and the other one is the CBC malleability vulnerability. The first one is the partial encryption. As you can see in this example, or the picture here, the object stream is the only piece that's encrypted, even when the PDF is encrypted, and the trailer actually gets the encryption information, and you can actually add more object streams that are not encrypted to within the encrypted PDF file. And here the researcher actually added created a new object stream, added this code. Basically, it just creates a submit form action when the PDF file is opened, unencrypted data, and sends it to the attacker's website. And that exfiltration channels typically used are form submission button, like this example, or link, or JavaScript. And the second vulnerability is the CBC malleability, and the requirement for this is a known plain text. And by design, Adobe actually provides that. To actually, there's a permission, 16 bytes of permission fields. This is where if you can print a PDF or something like that will be there. And for an encrypted one, it's encrypted using the same key. And the first 4 bytes are ones, and the second 4 bytes it's a p-value, and the next one is either T or an F, and the last 3 are A, D, B, and the last 4 bytes are random. So therefore we know 12 bytes of plain text based on the implementation, Now the attacker can either change the plain text, or the attacker can do some kind of exfiltration attacks within the encrypted. And majority of the PDF readers tested were vulnerable, and signing a PDF file won't work because the signature can be stripped, or it doesn't prevent the user from opening, or you can sign it with your own signature. And it's hard to close all exfiltration channels because they're used for legitimate purposes. And the ideal solution is to stop partial encryption and authenticated encryption instead of using AES, using encrypted DNS. Can you still understand or monitor where you are visiting? And two, there's EDNS has proposed some countermeasure to prevent these type of side channel attacks. And if those proposals are valid. And the researchers conducted two different type of scenario. One is the closed world experiment where the adversary knows the entire web page and they were just waiting to see if you're visiting any site and identify exactly what that site is. And the second one is open world experiment where the adversary only cares about a small piece of monitored websites and trying to understand if you are visiting one of those sites. And changing locations or any other variables did decrease the accuracy. However, it wasn't enough to prevent these type of attack. And the best countermeasure is padding. So therefore, ADNS recommends using 468 bytes block of padding. And here researchers attempted that and some other methods including DNS over Tor. And it seems DNS over Tor worked the best. And ad blockers works pretty well as well because they are blocking all the DNS requests that you would have made if it wasn't for that ad block. Four working components to the Let's Encrypt CA. The first one is IRSRG, which is responsible for day-to-day operation. ACME, Automated Certificate Management Environment, which is responsible for everything from certificate request to renewal, revocation, and issuance. And Boulder, that is open source ACME-based CA implementation. It's meant for secure, scalable, and high reliable operation. And Certbot, which aims to automate the installation of your certificate and make sure your web server is configured correctly for that. ACME is responsible for validation, and the validation methods are HTTP challenge, which is just uploading a file to your web server and verifying, and DNS challenge, just modifying your DNS record, and ACME verifies that. No human can issue a certificate, and they issue about 1 million certificates a day. And Certbot, it automatically configures Apache and Nginx by rewriting your config files and provides a better TLS secure configuration out of the box. Evercrypt, a fast verified cross-platform cryptographic provider, and their APIs are very simple to use, and they have the most comprehensive list of cryptographic tools that you can make use of within your application. And their libraries is comprehensive, and it has a wide variety of encryptions or hash functions or signatures that you can think of. The API design is meant to be agile, and therefore switching from one mode of operation to another, such as AES CBC to AES GCM, is fairly simple and straightforward. It just takes one line of change, and that's it. And all of their cryptography operation is mathematically proven to be free of memory, functional, and side channel attacks. Their implementation of Merkle tree implementation of Evercrypt is about 3 times faster than the current implementation of Bitcoin. And currently it's adapted by some of the major players, including Linux kernel. My final paper is Will Deleting History Make Alexa More Trustworthy? In this research, researchers were trying to see if users would feel better if they can delete the history of Alexa, if they would trust the device better and the content to be trusted, and also modifying like some other settings, would that make an impact towards privacy and trustworthiness towards the device. This includes speed, content length, and information source. And it turns out like when privacy setting was the privacy setting to delete the voice, non-tech savvy users seems to trust the device better, where the tech savvy users actually trusted less. It triggered some kind of privacy concern within their head just by showing them these controls, and so therefore it negatively reflected that. And combination worked based on individual privacy concerns as above, and letting users change contents actually lessen threats to privacy and content's credibility. The first paper identified gaps in password managers, including random password generation, encryption, and key derivation function implementation. And the next paper identified gaps in the PDF encryption implementation and how an attacker can exfiltrate an encrypted PDF file. And the third one used side channel attacks to identify or monitor DNS, encrypted DNS. Let's Encrypt certificate authority. All the websites in the world should be encrypted, and they are providing that service at no cost. And the EverCrypt is a library that aims to make implementation of cryptography functions simple. And and the last one is human behavior aspect when you're modifying privacy and security controls.